So I'm putting together a series of videos on Calc 1. I'll be focusing mostly on exercises, so like understanding the concepts and stuff like that should be something that people should already understand when they come to watch these videos, and mostly focusing on exercises, but while doing exercises also thinking about the concepts. But okay, so let's start. Also, the book I'm using is in the description of this video, and I'm currently on on page 76 of this book, and I'm going to be doing question 25. This is the page. The question goes like this: what is the limit as x goes to negative 3 from the right of x plus 2 over x plus 3. So we see that in the bottom we're getting closer and closer to 0. This is getting closer and closer to 0. And we know that if we have 1 over x, and if we want to graph this, we're going to have something that looks like this. And the reason is pretty simple. When you are approaching 0 from the right for this function f of x, when you are approaching 0 from the right, you get something like 1 over a really, really small number. Let's say 1 over a million. 1 over a really small number, which is the same as a million. And then you get even smaller, 1 over a billion. This would be, let's say, right here. You're going to get a number like that, because if you're going to have 1 over a billion here, then when you plug it into your function, you get 1 over a billion, and this will just be a billion. But as you approach from the left, so you get closer, you will have numbers like 1 over negative, or negative a million, which is negative a million, and 1 over negative billion, which is negative a billion, and that's why you're going very quickly to negative infinity when you're approaching from the left, and to positive infinity when you are approaching from the right. So every time you do a question like this, you need to think to yourself, am I going to plus and minus infinity? And if not, am I going to plus infinity or to minus infinity? And one of the things that you need to think about is is the numerator also going to 0? Because that if you have a constant over 0, then you could start thinking about, or this is getting closer and closer to 0, you can start thinking about, am I going to positive infinity, negative infinity, what's happening? And you're going to think about it in terms of this. But if both of them are going to 0, then you have to start doing different stuff. But in our case, so let's look at our case. We have again the limit as x goes to negative 3 from the right of x plus 2 over x plus 3. And you see that the numerator is not equal to 0 as you get closer and closer to negative 3. And this is equal to 0. So let's think about what's happening. So here you have your graph, and here you have negative 3. And we're trying to think about how the function looks as you get closer and closer to negative 3 from the right, from this side. So what happens is you're going to get x plus 2 over, I'm not going to change this x, but I'm going to imagine like what's going on at this x, and you're going to have something like a number really, really close to negative 3. So it can be something like, but a little bigger than negative 3. So it's going to be something, because we're approaching from the right, so it's going to be something like negative, I don't know, 2.99 ... then plus 3. So this number down here is positive, but really small. And this number up here is going to be negative, because you're going to have something close to negative 3 plus 2, which is negative. So you're going to have negative on top, positive on the bottom. you're going to have a really, really small positive on the bottom. So you're going to have a negative on the top. Let's think about it as a negative, and then let's just write on top, we're going to have a negative 1. Because that we're going to have something really close to 3 plus 2, we can kind of think about it as a negative 1, over something really, really small that is positive, let's say 1 over a billion. This is going to equal negative a billion. And you can keep doing this as you get closer and closer. This becomes smaller and smaller. 1 over a really, really small, a really, really big number, which makes this really small. So you're going to have negative 1 over a really, really small number, and this is going to get closer and closer to negative infinity. So this graph, when you approach from the right, is going to be going to negative infinity. And so the answer for the limit as x goes to negative 3 from the right side of x plus 2 over x plus 3 is negative infinity. If this was negative, this would be positive, because if this would be positive, no, sorry, this would still be negative, but this would also be negative, so your negatives will cancel. And if you just ask the question, what's the limit as x goes to negative 3 of x plus 2 over x plus 3, the answer is undefined, because it's plus and minus infinity, because it's going to do something like this. So that is that question. The next question I'm going to do is very similar. It's going to be problem, same page, problem 27. Problem goes as follows. The limit as x goes to 1 of 2 minus x over x minus 1 squared. So what is this? So again, when you have 1 over x, and you take the limit as x goes to 0, this is going to be plus and minus infinity, or undefined. But over here, so this is going to 0, right? The same thing would hold if I have, let's say I have the limit as x goes to 0, x goes to 1 of 2 minus x over x minus 1. This is also going to be plus and minus infinity, because down here we're going to 0, and up here we're going to 1. So it's going to be 1 over 0, very similar to this case, which is undefined, and its limit, and this is x, is just going to be plus and minus infinity, or again undefined. But over here we have a different case. We have squared. So again, the reason that we go plus and minus infinity is because that as we approach from the right, we're dealing with really, really small numbers. We're dividing by really small numbers, which are positive, and dividing a constant by a really small number, which is positive, gives you a really big number, which is positive. Okay? And as you come from the left, again, you're dividing a constant by a really small, but this time negative number, which gives you a really big negative number. C times the constant times the number. And this number is getting really, really big, a billion, a trillion, whatever, and so you go to plus and minus infinity. But in our case, from both sides, as you approach 1, as we're approaching 1, from both sides, so you are going to, so you're coming from this side and from this side, you're going to take the number and square it. So you're going to have a constant over, and then you're going to have a really, really small, when x is bigger than 1, so when you're from this side, you're going to have a really, really small number down here, so 1 over a billion. You're going to square it, which is going to give you just c over 1 over b squared, and that's just going to give you cb squared, a really big number. But the same thing is happening as you approach from the left. You're going to get a constant over a really small negative number, but you're going to square that number. And that's going to give you c over, and then the square is going to go on the negative, and that will become positive, and you're going to get 1 over a billion squared, and then that's going to equal c squared, which is again a really big number. So in our case, because that we are squaring the number, so the limit as x goes to 1, 2 minus x over x minus 1 squared, over here we have a positive number, over here we have a positive number, and then we have a positive number times a really, really big positive number as x gets closer and closer to 1 from either side, so this is going to equal positive infinity. Okay, the next example is also similar to these. I'm doing now problem 29, and this is the problem 29. So we have the, problem 29. We have the limit as x goes to negative 2 from the right, x minus 1 over x squared, x minus 2. So over here on top we have a negative 2 minus 1, so on top we're going to have a negative number, which is some constant, whatever, a negative constant. On the bottom, this is going to be positive, so we're going to have a positive, and it's going to be positive, and it's just going to be like close to 4. So this is, let's say, 4. And this is going to be a really, really small positive number because we're approaching from the right. And so we're getting like negative 1.99 dot dot dot, right? That's approximately what x will equal. So because of that, we have this number, and sorry, this should be a plus. We have this number plus this number, so this is a really small number. And so over here we're going to get a positive, really small number. So I'm just going to put just an epsilon to talk about a positive, really small number. And this is going to equal negative infinity. As this thing becomes really, really small for the same exact things we talked about, there's a negative here. So this becomes negative infinity. The next problem. So the next problem is a little interesting. Let's look at it. So this is problem 31. So we have the limit as x approaches 2 pi from the left of x cosecant x. So this is going to be the same, just by the definition of cosecant, as of the limit as x approaches 2 pi from the left of x over, x over sine of x. And over here we're going to have some constant again. It's going to be something getting closer and closer to 2 pi from the left. And over here we're going to have, and over here we have something really close to negative epsilon, a really small number. Why is this? So here is our graph, and sine goes like this, and then down and back up. And right here, when it's approaching from the left, it hits 2 pi at 0. So 1 over sine of 2 pi is the same as 1 over 0, which is undefined. As we approach from the left, so if we just took the limit of x going to 2 pi from the left of 1 over sine x, this is equal to 1 over a really, really small number, and this, as we talked about, is negative infinity. Now over here the only difference is that we have some constant on top. Over here we just have this constant, which is 2 pi, or approximately getting closer to 2 pi. So we get the same answer. So for 29, we get the limit as x goes to 2 pi from the left of x cosecant of x is equal to negative infinity. So the next problem we're going to do is a interesting one. So the next problem is x squared. So okay, this is problem 34, and it asks find the vertical asymptotes. So you have your function, and it might do stuff like this, and all of these are vertical asymptotes when it goes to positive or negative infinity at certain points. So, for example, we talked about the function f of x equals 1 over x, and its vertical asymptote is at 0 because it goes to positive and negative infinity. Here's negative infinity, and here's positive infinity. So find the vertical asymptotes of the function x squared plus 1 over 3x minus 2x squared. And we're not going to graph it, but we're going to find, so if we think about it, when will this function go to positive and negative infinity? So the only way for that to happen, nothing up here can really make that happen, simply because that x squared plus 1 can never really get to positive or negative infinity without x itself going to infinity. So yeah, so this thing will not be going to infinity. So what is going on is that there are certain times that this function goes to infinity or negative infinity when this is equal to 0, meaning when you have some constant up here over 0 down here, or something getting closer and closer to 0, and then the function goes either to positive infinity or to negative infinity or to both. So we'll have to see. So let's first find out where these places are. 3x minus 2x squared equals 0. We want to see where this is equal to 0. So then say something like x times 3 minus 2x equal to 0. So one time when this happens is when x is 0. Right? When x is 0, this becomes 0. So one vertical asymptote is x equal to 0. And the second one is when this is equal to 0, so we're going to have 3 minus 2x equal to 0. Or negative 2x equals negative 3. Or x equals 2 over 3. X equals 3 over 2. So that's another vertical asymptote. 3 over. So now let's do something a little bit more. So we know where the vertical asymptotes are. Let's try to figure out what the function looks like at a place. Meaning, so we have vertical asymptotes. Is it doing something like this? Is the function doing something like this at 3 over 2? Is it doing something like this? What is it doing at 0? So the way to do this is to pretty much take the limit. Or really it's to check, let's just take the limit from the positive side, from the negative side, so on and so forth. So let's do this for 0 first. So the lim as x approaches 0 of x squared plus 1 over 3x minus 2x squared. So let's first see what happens when we're approaching from the left. So from the left, this is positive, right? That is positive. And down here, what we have is we're going to have something negative, minus, and this is going to be positive because you can have x, which is negative, but squared is positive, so this is negative. So it's something negative minus something negative, which is really small, so it's positive minus something negative, which is really small. So the whole thing is going to go to negative infinity, right? Because you're going to have something positive, which is a constant, over specifically 1 over here, because of this 1, and this x doesn't really count, it's really small, over something really, an epsilon again, something really small, which is negative. So, yeah, so we're going to get a negative infinity. When we're approaching from the right, so again, this is 1 up here, and this is going to be positive. This is going to be positive 3 times some really small number, and then we're going to take minus 2, and then over here the number is going to be even smaller, and the 2 is multiplying, right, because we're going to have a really small number, epsilon squared, which makes it even smaller, right, if we have 2 over 3, meaning a number less than 1. And over here we're taking x to be much smaller than 1, and we square it. This becomes 4 over 9, so it becomes even smaller. So we squared it, so the x becomes really small. Multiplying by 2 doesn't really help. The number is going to be positive down here. So even though there's a negative over here, this number, 2x squared, is going to be smaller than 3x when x is really, really small. And so because of that, the number up here is going to be positive. So we have a positive number over a positive, really small number. So this is going to be infinity. It's going to go to so when we're approaching from the right, we're going to positive infinity. And then the other case, I'm not going to do it. I'm not going to do the other case. The 0 is enough for now. Okay, now looks like an interesting problem. Problem 40 on page 77. Page 77. Problem 40. In the theory of relativity, the mass of a particle with velocity v. So the mass of any given particle is m0 over 1 minus v squared over c squared. And we're told that m0 is the mass of the particle at rest. So once the particle is not moving, that's its mass. C is the speed of light. And now we want to know what happens to the mass of the particle as v approaches c from the left. So v gets closer and closer to c from the left. So when v gets really, really close to c, but is not exactly c, so it's a little less than c, right? So we have v is very close to c, but it's still less than c. But still it's getting really close to c. So v squared over c squared is getting closer and closer to 1, but it's a little less than 1. So it's like becoming 0.999 dot dot dot. It's getting really close to 1 because v is getting really close to c, but it's not exactly 1. So we're going to get m0 over, and then here we're going to have a really small number because we're going to have 1 minus, let's say 0.999 dot dot dot, like something really close to 1. So again, an epsilon, it's going to be positive because the 1 is positive, and we're saying minus another number really close to 1, but a little less than 1. And so this whole thing is going to be infinity. The limit, so we can write more rigorously, limit as v approaches c from the left of m0 over 1 minus v squared over c squared is equal to infinity, which is kind of what we know, that if we take something and we make it go as fast, get closer and closer to the speed of light, then its mass is going to get closer and closer to infinity. The interesting question we can ask, and this is impossible, but what happens if we're approaching c from the right? So v is bigger than c, and v is getting very close to c. So then we're going to have v squared over c squared again is going to 1, but it's going to go to 1 and always be like a little bigger than 1, because the v is bigger than c. So because of that, you're going to have m0 over 1 minus v squared over c squared. This thing is getting closer to 1, but it's always a little bigger than 1. So this whole thing, 1 minus something a little bigger than it, is some really small negative number. So really small negative number. This square root doesn't really matter. m0 over something really small but negative. And we know that this, as epsilon goes to 0, so epsilon goes to 0, this goes to negative infinity. So if we're getting closer to the speed of light, if the velocity is getting closer to the speed of light from the right, the mass of the particle is going to be negative infinity, which doesn't make sense, but who cares, right? Fine. So now moving to the next section, page. So the exercise in the next section, page 84, and I'm going to do problem 1. Why not? Just to see how the rules work. So we have given that the limit as x goes to 2, f of x equals 4, and the limit as x goes to 2, g of x equals negative 2, limit as x goes to 2, h of x equals 0. So first find, so for a, find the limit as x goes to 2, f of x plus 5g of x. So just using the limit laws, the first one first in page 77, and then the rule regarding constants, which is on page, which is the third law of the limit laws on page 77. We can basically put the limit inside, so we have it's the same as the limit as x goes to 2 of f of x plus 5 times the limit as x goes to 2 of g of x, and the rest you can solve because we know what this is, we know what this is, we multiply it by 5. I'm gonna, well, C, let's see, I'm gonna skip B. C, the limit as x goes to 2, square root of f of x, using the rule 10 on page 79, sorry, using rule 11 on page 79, we can just put the limit inside the square root. We just take n equals 2, put the limit inside, so it's the same as square root of limit as x goes to 2 of f of x. The rest you can solve. Careful, we need to be careful with e. So with e, when you have the limit as x goes to 2 gx over hx, so you cannot say that this is the same as the limit as x goes to 2 of g of x over the limit as x goes to 2 of h of x. And the reason you can't in this case is because of this is 0. So the limit doesn't exist. Anything else? Okay, we're going to skip the rest. Just to do a concrete example, example 7, we have the limit as x goes to 1 of 1 plus 3x over 1 plus 4x squared plus 3x to the 4th to the 3rd power, and by rule 6 on page 79, we can put the limit inside, so this is the same as the limit as x goes to 1 plus 3, so let's just put in what 3kx over 1 plus 4x squared plus 3x to the 4, all this to the 3rd power. And then we know that rule, I mean, yeah. Assuming that we are not dividing by 0, in which case, assuming that by plugging in x we're not going to be dividing by 0, we can just plug this in. I mean, there won't be any problems, so we can just plug this in. We're going to have 1 plus 3 over 1 plus 4 plus, is that a 3, plus 3 all to the third power, and that's what the limit is. That's not equals, yeah, that's what the limit is. So problem 10 asks what's wrong with the following equation: x squared plus x minus 6 over x minus 2 equals x plus 3. And the problem with this is, so this comes about when you say something like, okay, x minus 2 times x plus 3 equals, and then you have, right, x squared, and then x squared plus 3x minus 2x minus 6, which is going to be equal to x squared plus x minus 6. So you would say something like, listen, x minus 2 times x plus 3 is equal to x squared plus x minus 6. So why can't I then say that x plus 2 is equal to x squared plus x minus 6 over x minus 2, right? Why isn't this true? Well, it's not true because that you might be dividing by 0. X minus 2, if let's say x equals 2. Let's just plug it in. So let's say you have, let's say you made that claim, x squared plus x minus 6 over x minus 2 is equal to x plus 3, and then you take x2 equal to 2. So then you're going to have 4 minus 2 minus 6 over 0, and this is undefined, is equal to something very defined, which is 5. So, right, you would say, wait, there's a problem here. And the problem came about because that over here, when you went from this step to this step, you might have been dividing by 0. So you can't. But now what you can say is that the limit as x squared plus x minus 6 over x minus 2, the limit should be equal to the limit as x goes to 2 of x plus 3. Because now, this is x goes to 2. Because now you're not dividing by 2. You never actually touch 2. You're taking the limit. You're getting closer and closer to 2, but you're never actually touching 2. And when you do that, now, so you basically can say the limit of this side as x goes to 2 is equal to the limit, the same limit at this side, and then you can divide because you're dividing by 0, so this should be true. So this limit should equal this limit, which is 5. So the limit for this thing should be 5. And this is a plus. And so in question 11, right, in question 11, they actually asked this. Question 11 on page 85. What is the limit as x goes to 2 of x goes to 2 x squared plus x minus 6 over x minus 2? And we know that the answer to this is 5. One way to actually do this is to say, listen, x squared plus x minus 6 is equal to x plus 3 times x minus 2. So this thing is equal to x plus 3 times x minus 2 over x minus 2. These cancel, so this is equal to x plus 3, taking the limit as x goes to 2. If x plus 3 is equal to 5. So this limit is equal to 5. So the next problem seems similar. So problem 13 on the same page. We have x squared minus x plus 6 over x minus 2. And we want the limit x goes to 2. It seems similar, but the only reason that in problem 11 we got a constant even though we were dividing by something that was approaching 0 is because that in the numerator we were also approaching 0. So we kind of had like 0 over 0, and this is not defined, but if you have a limit, then you might get some number out of this. But over here, this is going to equal plus and minus infinity for the simple reason that if you just look at the limit as x goes to 2 of x squared minus x plus 6, this is equal to 4 minus 2, 2 plus 6, 8 I believe, which is not 0, so you're going to have 8 over something approaching 0, right, lim as epsilon approaches 0, and this, as we have shown a couple of times, is plus minus infinity or undefined. So that's why this problem from the previous one. So the next one requires, so problem 15, a pretty interesting subtle realization. So we have the limit as t goes to negative 3, t, sorry, my thing just turned off, t squared minus 9 over 2 t squared plus 7t plus 3. So t squared minus 9 is equal to t plus 3 times t minus 3, right? That times that is t squared, and then t minus 3t is negative 3t, and 3 times t is plus 3t, and these cancel, and then 3 plus 3 minus 3 times minus 3 is minus 9. So that's that. And then also 2t squared plus 7t plus 3 is equal to 2x plus 1 times x plus 3, right? Because, okay, 2x times x is 2x squared, and then you have plus 6x plus x plus 3, x, these are supposed to be t's. So, yeah. So that is equal to 2t plus 1 times t plus 3. So now let's put it together. So this is going to equal t plus 3 times t minus 3 over 2t plus 1 times t plus 3. These cancel, so that becomes equal to t minus 3 over 2t plus 1. Take the limit as t goes to negative 3. So let us plug let us plug in the negative 3. So this becomes negative 6 over, this becomes negative 6 plus 1, so negative 5, which is equal to 6 over 5. So that's the limit. The limit is 6 over 5. Okay, next problem. So the next problem we're going to do is problem 17, which is the limit as h goes to 0 of 4 plus h squared minus 16 over h. So this is equal to, so we're going to have 4 plus h times 4 plus h, which is equal to h squared plus 4h plus 4h plus 8h plus 16. That's that. So this becomes, so this, go over here, becomes h squared plus 8h plus 16 minus 16 over h. The 16's cancel, so that is equal, let's take out an h, so it's equal to h times h plus 8 over h. The h's cancel, so this is going to equal, so we have the limit, what's the limit? So h goes to 0 of h plus 8 over 1, so this just becomes 8. So the limit of this thing is 8. Okay, problem. So the next problem we're going to do is problem 19. And there's like a little thing you need to realize eventually in these problems. Like, they are trying to do something that you can solve. So you just need to think about it. So x goes to negative 2, x plus 2 over x to the third plus 8. So what you can assume is that you can turn x to the third plus 8. You can make this equal to x plus 2, so that this and this cancel, times some other number, times something else, and that's what you'll be left with, right? Just, we can assume that you can do that because they're trying to help you out. They want you to be able to solve this. So just say, okay, I'm going to write x to the third plus 8 into x plus 2 times some number. So how do you find this number? Well, you already know a lot of what's going on, a lot of what you need. So we're trying to make x plus 2 times some number to be equal to x to the third plus 8. So the first thing we're going to try to get is the x to the third. So in order to do that, you need an x squared over here. So you're going to put an x squared over here. And then now let's write it out. So now what we have is x to the third, and then you're going to have the 2, and the x squared is going to give you plus 2x squared. But you don't want this, so what you're going to have to do is you're going to have to take negative, and then you can take this, multiply it by something, specifically 2x. So x times negative 2x is going to give you negative 2x squared, and these are going to cancel. But now you're going to take your 2, and you're going to multiply it by your negative 2x, and you're going to get negative 4x, and we don't want that. But you can add plus 4, and then the x times, when you take the x times 4, you're going to get a plus 4x, and these are going to cancel, but now the 2 again multiplies with your 4 and you get plus 8. That's exactly what you want, so this is the number you're looking for. So x plus 2 times x squared minus 2x plus 4 is going to give you x to the third plus 8. And just go through the steps. Do this times that. Think about what you need in order to get x cubed. Write that in, and then think about, well, but you got something new, because that when this number is multiplied by that number, you're going to get something new. So you're going to add something in order to get rid of that. So this multiplied by that will get rid of this, but then you're going to get something else. So on and so forth, you're going to keep balancing it out until you hope that you will end up with what you're looking for, because they want you to succeed. So that's what we get. So this is going to equal to So let's just, so this is x plus 2 over x plus 2 times x squared minus 2x plus 4. These cancel, and you're left with, so now let's just plug in the negative 2, right, because it'll get 4. Yeah, you should be, yeah, you can just plug it in. So you're going to get 1 over 4, sorry, 4, 1 over 4 minus, which is plus 4, plus 4, so this gives you 1 over 12. So that's your limit. Very nice. So again, the trick is, know that they probably want something over here when you expand it to cancel with this. Assume that that's true, and just try to figure out what you would need in order to do this. And you just do that by starting, take x times some number, what will give you the x cubed, write that in. But then when you have 2 times that number, that will give you a number, you add that in. You have to get rid of that number if it doesn't exist, if it doesn't appear here. So you're going to basically keep adding different values over here and changing them, so eventually you end up with this equality. Yeah. Okay. Next problem. So now problem 21. For problem 21, we are going to do something similar. 9 minus t, taking the limit as t goes to 9 over 3 minus square root of t. So if you take square root of t, so, take 3 minus the square root of t times 3 plus the square root of t, right? Because over here we see a 9, we see a t, we don't see anything in the middle, we don't see like the square root of t times something. So this is the form that will give that to us, as we'll see, because that we're going to get 3 times 3 is 9, and then over here we're going to get minus 3 square root of t, and then plus, sorry, this is a t, plus 3 times the square root of t, and then minus the square root of t. Minus t, right, when the t's multiply, right? Because when you have a minus and a plus over here, basically these are always going to cancel. So you're going to get 9 minus t for that. So this can be written as 3 minus the square root of t times 3 plus the square root of t over 3 minus the square root of t. These cancel. You plug in your 9. So this is going to be, you plug in your 9, you get, so this is going to be 6. So that's the answer. The limit is 6. It just occurred to me that they have the solutions for all of the odd numbers in the back and not for all the even ones, and I've just been doing a bunch of odd ones, I think. So I'm just going to do mostly even ones from now on. I mean, if I see a nice odd one, I'll do it, but I guess if they have the solutions, or at least the numbers for the solutions, I don't know, it's better if I just do the even ones. So let's just do one of the, what they claim is the harder even one, and we'll move on, and everything else is basically the same. Maybe I'll do 2 even ones. So let's see the limit. This is problem 20. Limit as h goes to 0 of 2 plus h to the third power minus 8 over h. Basically, you're going to expand this. You're going to see what it is, and you're going to see that the 8's are going to cancel. And, okay, so let's do it. So 2 plus h times 2 plus h. This is just going to give you 4. Then you're going to have plus, then 2 times h, plus 4h, plus h squared. And then when you take this times 2 plus h, you're going to get 8 plus 4h plus 8h plus 4h squared plus 2h squared plus h cubed. And okay, so now let's just imagine, okay, so this is that right there. Let's just put the rest of the problem in. Minus 8 over h, limit as h goes to 0. This 8 and that 8 cancel. We can take out h's, so we're going to be left with h times 4 plus 8 plus 4h plus 2h plus h squared over h. These h's cancel. Because we have the limit as h goes to 0, this vanishes because we have 4 times 0, 4 times 0, 2 times 0, and 0 squared. So this just becomes 12. That's our limit. Does that make sense? We have 3h squared, plugging in 2. Yeah, makes sense. Perfect. Okay, next one. What problem? Let's see problem 26. The limit as t goes to 0 of 1 over t minus 1 over t squared plus t. So let's first find the common denominator. This is equal to x squared plus t squared plus t minus t over t times t squared plus t. This is from finding the common denominator, right? We multiply both of the multiply this and this by t squared plus t, and we multiply both of these by t. So then on the bottom we have the value t times t squared plus t, and now we can do the minus part, put them together. Okay, so this is the same as t squared over t times t squared plus t, and these are going to cancel. And now this is the same as t, and we can take out a t from here, so we're going to have t times t plus 1. And now these t's are going to cancel. So this is the same as 1 over t plus 1. And now as t goes to 0, this is the same as 1. So the limit of this is 1. Okay, so the next problem, I'm not going to do the graphing. This is problem 31. It's odd, but maybe... No, I'll just do it. I'm just going to do part C. So we have the limit as x goes to 0, x over square root of 1 plus 3x minus 1. So now let's just multiply the bottom and the top by conjugate this, which will be square root of 1 plus 3x plus 1, square root of 1 plus 3x plus 1. So we can get rid of the square root in the bottom. And this is going to give us x times, let's just write this one out, 1 plus 3x plus 1, like that, over, okay, so in the bottom we're going to have square root of 1 plus 3x minus 1 times the square root of 1 plus 3x plus 1. This is 1 plus 3x minus plus 1 plus 3x minus 1 plus 3x, and then minus 1. So the 1's cancel. We get a 3x in the bottom, 3x. The x's cancel. So we get square root of 1 plus 3x plus 1 over 3. For 0 this vanishes, so we get 2 over 3, which is our limit. Okay, next problem. Okay, now I'm going to do problem 33 using the squeeze theorem. Maybe I should just quickly state what the squeeze theorem says. So this is on page 83. If we have a function, if we have the condition f of x is less than or equal to g of x is less than or equal to h of x, when x is near a for all x near a. So let's say this is a over here. This is where we're trying to find the limit. For all of these, we have the following condition for all x's near a, except for maybe at a, because we don't care about that. And we know that the limit as x approaches a, f of x is equal to the limit as x approaches a of h of x, which is equal to L. Then we know that the limit as x approaches a of g of x is also equal to a, meaning, okay, so you have, let's say, a function g of x, and we don't really know what the limit is. We're trying to find the limit, let's say, right here. And we have another function f. We have another function f of x that maybe does something like this, and is always bigger than g of x. And then we have a function h of x that always does something like this. It's always less than g of x. Then we can, and we know that the limit for both of these functions right over there is L. They kind of touch. They touch right when they get closer and closer to a. These two functions touch. Okay, so this is right at a. Right at a, they're touching. Then we know, because, so they're squeezing black. Black must go like that. So black, or g of x, has the same limit at f as at a. So, okay, so in our problem, problem 33, they ask us to find the limit. So x goes to infinity of x squared cosine 20 pi x. They want us to show that this is a 0 by squeezing it by negative 2x, negative x squared, and x squared. And why is this squeezing this function? So cosine of 20 pi x is always greater than negative 1 and less than 1, because cosine is bounded by negative 1 and 1. Whatever, negative 1, kind of whatever. I don't know, cosine. So this is 1 and negative 1. Cosine is bounded by negative 1 and 1. And so this is always between negative 1 and 1. And so this function, so we can multiply both sides. So we have negative 1 is less than cosine 20 pi x is less than 1. So now we can multiply everything by x squared. So we have negative x squared is less than cosine 20 pi x, which is really less than or equal to x squared. So now these two functions, we can look at this as f of x, this function g of x, this function is h of x, and f of x and h of x are squeezing g of x. And the limit for f of x and h of x, meaning the limit as x approaches 0 of x squared is equal to the limit as x approaches 0 of negative x squared is equal to 0. So therefore we know that g of x, which is equal to x squared cosine 20 pi x, its limit is 0. When we make the when we do stuff with the equalities, we have to be very careful. So this works. If you have, let's say, -1 is less than cosine x, which is true, which is less than, which is, and this is less than 1. So now we can say, okay, so -x squared is less than cosine x is less than x squared, there. So this is true. But the following we can't do. We cannot say that -x is less than x cosine x, which is less than x. This we can't do. Because that when we multiply over here, when we multiply this side and over here by x squared, we're always multiplying by a positive number. And so the inequalities never change, right? Because x squared is always positive. So we can do this and the inequalities remain the same. But over here, x is sometimes positive, sometimes negative. If you just take f of x equals x, that's a line which is sometimes negative and sometimes positive. So when you multiply by a negative number, the inequalities flip. So there might be parts over here where we had to flip the inequalities and we didn't. And the fact of life is that this is simply not true. If you graph it, you will see that -x is not always less than x cosine x, which is not always less than x. So you just need to be careful when you do this trick to always make sure that you're multiplying by a positive number, or you're always multiplying by a negative number and you flip the inequalities at one time. But if sometimes you're multiplying by a positive number and sometimes you're multiplying by a negative number, you can't really do any of this. Yeah. So I am going to stop here. I'm going to start a new video, and I guess I'm going to do problem 34. Hope this was helpful. Most of what I want to do in this series, in these videos, are just going through a lot of examples with limits, derivatives, integrals, anything to do with Calc 1, maybe L'Hopital's rule. So we'll see, and just a lot of examples. I don't really want to focus on the concepts as much. I might do some epsilon delta definition stuff. We'll see. Okay.